This is Michelle McIntire, Lab 4, Section NO3. The objective of this lab was to take a video, analyze it, and create a model to predict the motion using Newton's second law and verifying with the energy principle. We were able to successfully predict the motion. Also, we found an oscillation period from the tracking video. The initial conditions had the initial position based on what we got from the tracker. Initial velocity was 0, which it was released from rest. The mass is 0.402 kilograms. The spring constant is 6.83 newtons per meter, which we found in the practice lab. Weight force, 9.8 meters per second. Alright, then we went to tracker. We calibrated the video based on the length of the spring, which is 0.7 meters. Step 2, we set the frames to start at frame 6, which is the moment of release. Step 3, we tracked the objects with auto tracker. And step 4, I output the X and Y values to a CSV file to use later in the Python model. Okay, next thing we did is we input all of our initial conditions into Python. This is it. Ball position is that first position that we have at time t equals 0. And ball.v is 0. This is the initial system conditions. KS, all of the other, and then also we have our initial energy system. Also L-hat, L-mag, and change in S that we need for the spring force. Next we did our calculation loop, and the force of the spring was KSS squared times L-hat. F-net, F-grav, plus F-spring, which is the total force. And according to Newton's second law, F equals ma, and F-net is equal to the sum of the forces. So basically we got velocity from the acceleration and the position from the velocity to update that. And we also updated the value of L for the next point. Next in Python, we validated with the energy principle, and K initial we set to the K going into the loop. And then at the end, K is equal to 1/2 mv squared, UG mgh, and US is 1/2 KSS squared. So what we did there is we added everything together to get the total energy, and this is how we're going to verify our model to verify the energy principle. Okay, and this is the final tracker data with the arrows pointing out the spring force and the gravitational force. Also, we have the oscillation graph on the bottom, and you can also see the track of the object as it went around. It almost makes kind of a rectangle. To the left, you see the code for the arrows specifically, so you can see how those were created. Okay. Next, we compared tracker to Python, and I had an error because, of course, nothing works perfectly. I added import to the startup for the importing the CSV file, and I also imported the data to read, but it didn't exist, and I don't know why, because as you can see, it's listed in the same folder as my program, and I also had it open at the time, and it's the exact same name. So if you know what's wrong, tell me. Energy principle satisfied. The blue represents the total energy, red represents kinetic energy, yellow represents gravitational potential, and green represents spring potential. So from this, it verifies the energy principle because, as you can see, the yellow, red, and green lines all add up to be the value of the blue line, which is a constant energy, meaning there was no work done on the system externally. Next, we did the oscillation period, which is for X. We just took the 5 different peaks, and we also found the T initial and T final of each of those peak points. I did the total change in time divided by the number of oscillations for this value here you see, and did the same thing for Y, except there were 6 peaks, and I took those different values and got a similar thing. The numbers, the period for X was marginally greater than the period for Y. This could have been accounted for by error in placing the tracker points. Also, any friction. So also the motion satisfied the energy principle, therefore the net force acting on the system is 0. And that concludes my lab 4. Thank you.